Hi everyone. So I've selected a few topics from chapter 1 that I find to be the most important things going forward in this class. So in this class we're going to study the elements and how they cycle through the environment. So I'm going to hit on concentration units, also talk a little bit about isotopes, and then go into box models and geochemical cycles. So with respect to units, there are many different ways to frame the concentration of an element or a chemical compound. And depending on what field you're in, you're going to be using different units. So in terms of, say, molarity, big M, moles of solute per liters of solution, that is really a chemistry concentration unit. Chemical oceanographers also use molarity, usually in terms of micromolar, very small amounts of molarity. And I would also say that in environmental fields like engineering, environmental science, probably even geology, they use more of a parts per million type scheme. And so let's go over these units that I have on this board, and then we'll do a couple examples. And so the goal here, in the end, after you understanding how to calculate units, is you should be able to convert from one type of unit to another with relative ease. And so molarity, to start, it's pretty much just a solution-based concentration, meaning some sort of solute, a solute being the substance that becomes dissolved, and that is in a volumetric unit of liters. So it's moles of solute per liters of solution. Now when we get to units such as parts per million, parts per billion, and parts per trillion, they're a little bit more flexible in how you can frame that unit. So for example, for parts per million, it can either be a weight volume unit or a weight unit. So for solutions, say we're going to dissolve a certain amount of milligrams of something in a liquid like liters. So milligrams per liters, as I'll show you in the next slide, is a unit of parts per million. But again, depending on what field you're in, maybe you'll read a research paper where parts per million is in micrograms per milliliter. But again, that is still parts per million. If we're looking at, say, soil samples or some solid sample, it might be in a weight unit. So very common for soil samples, parts per million is milligrams per kilogram. That is 1 part per million, as is micrograms per gram. So with respect to parts per million, it can either be micrograms per liter for weight volume or nanograms per gram. Right there, nanograms per gram. Parts per trillion, even smaller, nanograms per liter, picograms per gram. And so how is a milligrams per liter a ppm, a parts per million? Well, it's assuming that 1 liter is 1,000 grams. We know that for every mil of water, it weighs 1 gram. So 1 liter is 1,000 grams. And 1 milligram, this milligram here, is 0.001 grams. So milligrams per liter is 0.001 grams over 1,000 grams. That ratio is 1 to a million, or 1 part per million. We could do this type of calculation for any of those units on the previous slide. So let's do some calculations. Let's calculate molarity, parts per million, and parts per billion of copper in a solution containing 0.512 grams of copper chloride in water with a final solution of 500 mils. While we do this calculation, we will mind our significant figures and report our result with units. So this might be a good time for you to stop the video and maybe perhaps try to do these calculations on your own. So molarity, defined as moles of solute per liters of solution. The best way to approach this is to just find each of these values separately. We already know the final volume of the solution, which was 500 mils. We convert it to liters, so we have this number here. Now we need to find the moles of copper. Remember that we're not interested in moles of copper chloride. We want to know the moles of copper. Sometimes it may be the same, but nevertheless, we need to consider what the question is asking. So I start with my grams. This is what I know. I have 0.512 grams of copper chloride. I use the molar mass. I use the periodic table to add up the masses of all of these elements. And I get the molar mass of 134 grams per 1 mole. And then I use stoichiometry. And I say for every 1 mole of copper chloride, there's 1 mole of copper 2+, or just copper in general. And I see that my units cancel here, and I'm left in moles of copper solute. And so that's the number I put here, and I divide by my liters, and I get my answer. 3 significant figures because of the initial volume or initial grams that I started with. So ppm, I'm going to use the same approach. I'm going to use milligrams per liter. And what we have here, I need to find the milligrams of copper to start. So again, I use the 0.512 grams. I get into moles. I want to get into moles of copper. And once I do that, so essentially this calculation up to this point is similar to what we covered up here. I then use the molar mass of copper, which I get off the periodic table. Copper weighs 63.55 grams per mole. And now I'm in units of grams of copper. You see all these units cancel out. And I'm left in grams of copper. And now I just use this conversion to convert to milligrams of copper. And I get 242 milligrams. I divide that by 0.5 liters. And I get 484 parts per million, or milligrams per liter. So lastly, I can convert the ppm into parts per billion by just changing the unit. So here's my parts per million answer. And I'm going to say for every 1 milligram, there's 1,000 micrograms. So a microgram per liter is a parts per billion. And so here's my final answer. 4.84 times 10 to the 5 parts per billion. So again, you should be able to go backwards and forwards, say changing molarity into parts per million, and vice versa. So I want to do one more problem, and I'm doing this problem to make a point about these units. So let's determine the molarity of a 5 ppm solution of arsenic and a 10 ppm solution of lead. So right now we would probably say that the 5 ppm arsenic solution is less concentrated than the 10 ppm lead solution. And it's actually half as concentrated. And that's perfectly reasonable. But let's convert these units into molarity. So let's start with our 5 milligrams per liter, and we change it to grams. We then change it to moles. So now I have liters and I have moles. I'm in moles per liter because all the other units cancel out using dimensional analysis. And so to one significant figure, I get 7 times 10 to the negative 5 molar, or 70 micromolar. I do the same thing with lead, and I get 5 times 10 to the negative 5 molar, or 50 micromolar. So which is more concentrated? Well, again, it depends upon what unit you're using. And of course, I selected 2 elements that would give me this unusual answer, but it does show you how different these units are. Molarity is in moles per liter, so it is telling you how numerous the element is in a certain volume. And in some ways, I would argue that that is more accurate in terms of concentration. How much you have in there, how many you have per liter, is a better measure than how much mass you have in a volume. And so parts per million, parts per billion, it's all about the mass. How much mass of a certain element you have per volume. And the reason this example worked the way it did is because lead is so much more massive than arsenic. It's over twice as massive. And so the units in parts per million is greater given the numbers that, as in terms of how many atoms per liter there are. So just consider that when you use different units and what they mean. So here we have lead at 207.2, and then here we have arsenic up here. And so they're not that much different in mass. I could have come up with the even more extreme situation. But just so you know, units vary and you really need to know what they're telling you. The last topic of this short video is to kind of just recall what these average weighted masses are on the periodic table, where they come from, and what kind of information is in these numbers. And so I just want to remind you that those numbers of the average weighted molar mass, it's actually the average of all the isotopes. And I want you to start thinking of isotopes because the different isotopes will come into play when we talk about different environmental processes. So here in my example, iron, it has a molar mass of 55.845 AMUs, or more commonly, we use the unit of grams per mole. And both units fit this number, but we commonly work in grams per mole. So iron has 4 stable isotopes, but they all have different abundances. And so iron 56 is the most abundant at 91.7%, and then the other isotopes are a fairly low abundance. And so what we'll find is we can actually study the elements and how they cycle by looking at the different isotopes. So what nature does in many cases, no matter if it's a physical transfer, say like evaporation, or it's a metabolic push in an organism, such as metabolizing nitrogen as a nutrient. All of these things actually end up fractionating the elements by their isotopic weight. For example, you can imagine in evaporation that if the water molecule is slightly lighter, maybe it has more isotopes of hydrogen and oxygen that are lighter, say oxygen 16, hydrogen 1, relative to heavier isotopes like oxygen 18 and deuterium. What we'll find is that there's actual fractionation where the lighter isotopes will evaporate in a greater percentage than heavier isotopes. Same with the metabolic use of nitrogen. Organisms will use nitrogen 14 in a higher percentage than they do nitrogen 15. So we can play with the isotopes, and their fractionation and use as tracers even is really important. I used iron 57 as a tracer, so it's only 2% of the abundance of the average iron in the environment. So what I did when I was in the Bering Sea is I did shipboard experiments where I used the low abundant isotope of iron 57 to trace how phytoplankton take up iron and also regenerate, meaning after they're done using it, it goes back into solution. And I was able to use the iron 57 to follow cycling. And so I ended up putting the iron 57 in the water in these bottles, and I watched the iron 57 go into the phytoplankton as they grew. But what I was also able to do is watch the iron 56 go back into the water. And so over the course of this 5-day experiment, I used the low abundant isotope as a tracer, and I was able to get at rates of assimilation, which is rates of uptake, and also the rate of regeneration, meaning how much was actually going back into the solution. And so these are questions that oceanographers are interested in, and I use the play of iron 56 and iron 57 and their relative abundance. And so last, what I would like to just briefly talk about is how that average weighted mass is calculated. So essentially, all we need to do is sum up. All we need to do is sum up the masses and multiply them by their fractions. So we take the mass of each isotope, times it by its fraction, and sum those terms up, and that will equal the molar mass. And so we'll take our mass of 56, iron 56, times it by its fraction. So note that I changed the percent into a fraction. Mass of 57 times the fraction, and so on. And that's where we get the 55.845 grams per mole, or AMU. And here's a total fraction of 1.